So this should be the last video lecture for 12.2, and all we're going to do is we're going to look at some properties of derivatives. We're going to look at vector valued functions. We're going to look at some properties of integration for vector valued functions. We'll do an application question, or actually, I think we'll hold off on application. We'll probably just do an initial condition type problem. Nevertheless, let me jump in. So the good news is the majority of your derivative formulas that you had learned in Calc 1 all apply to vector valued functions. Only the things that you have to highlight are the ideas of, say, property 4, property 5. We were not, in Calc 1, we weren't dealing with vectors. So you had no practice with, say, a dot product of vectors. So, in other words, you would have had no practice with the derivative of a dot product of two vectors, or a derivative of a cross product. But you can see that the math, I mean, as you can see, this very much resembles a product rule, right? Except be careful because this is the dot product here, and this is the cross product here. So I would advise you to read through and make sure you understand each of these. Just keep in mind that for 1 through 7 of this theorem, the r and the u, these are vector valued functions. But if you see a w, right, a w, this is a real valued function. And when we say real valued function, again, just think back to functions like f of x, the functions that we were exposed to prior to this class. And then, of course, you have some scalars as well. I'm going to do, so for example, there's two parts, part A, part B. Part A uses property 4 from the previous page. Part B uses property 5. I'm just going to do part A for you, and then I'll just give you the answer to part B. If you happen to have any trouble with that, you can always reach out to me. But nevertheless, let's go ahead and get started. So what we are given, two vector valued functions, and we are asked to find the derivative of their dot product. Okay. So we got to be careful, because I can see myself in haste just taking a dot, and then taking the derivative of a dot product, which would be absolutely wrong. You want to make sure you follow the recipe here, which I will just present without a lot of elaboration. Well, let's look at the recipe. What is required? Well, we need r. We have that. We need u. We have that. We definitely need u prime and r prime. So we'll go ahead and get those right now. All right, starting with r prime. All right, well, we're going to go through this as quickly as possible here. So r prime would just be, well, we got 1 over t, so that would be t to the -1, so that should be -1 over t to the power of 2i plus, well, what do we got? ln, so the derivative of ln with respect to t is just 1 over t. All right, let's go ahead and jump to u prime. So what do we got? We got, for u prime, we just have t squared. So, okay, so that's easy. That's just going to be 2t. Then we have the derivative of -2t, which is just -2. And the derivative of 1, or just k, would just be 0. I'll go ahead and write that as plus 0k, just so that you know that that 0 is attached to the k direction. Okay, well, what is left to do is to go ahead and take the dots, right? So we would be taking the dot of r and u prime. So here's r, here's u prime. We need to take the dot of that plus the dot of r prime u. I'm going to go ahead and just jump into this. So we got 1 over t times 2t plus negative 1 times negative 2 plus ln of t times 0. All right. So assuming there's no silly mistakes, that will be, I'll go ahead and actually write it above. That is the dot product. I'll go ahead and write it. This is r of t dot u prime of t. Okay, so we know that part. Now let's jump into r prime of t dot u. Okay, let's see if I can write it without running out of space. So negative 1 over t squared times t squared plus 0 times negative 2t plus, oh, that was definitely too ambitious, wasn't it? To be able to get all of this in one line. Let's try this. See the things I do for you guys? Do you see this dedication on my end? Right? 1 over t times 1. All right. So I agree with you. We got to clean this stuff up. So we got a series of, just multiplication and addition. Let me go ahead and I got 2 steps to the solution. Ready? So this is just going to end up being, I'll use the same color. So this is going to end up being 2 plus 2 plus 0. And then we're going to have, finish this up. So what is that? That's just going to be negative 1 plus 0 plus 1 over t. All right. There's nothing left to do except combine like terms. So we've got 2 and 2 is 4. We take away 1 is 3. And then we just have 1 plus 1 over t. All right. So is this a vector? No. Is it a function? Yes. So again, I mentioned this in passing in the previous video, dot products of vector valued functions. I'll say it slow because you might be daydreaming. The dot product of a vector valued function could be a function. It just will not be a vector function. So right, there's no I, J, K in here. All right. So I mentioned that I would go ahead and give you the answer to part B. So I will produce it here without any elaboration. The answer, part B, you should get 2J plus 4TK. And that makes sense because you did a cross product for part B, and you know that a cross product should give you a vector, in which we did get a vector. So some notes on integration. Now, again, you may find, and it is understandable, right? You have digested, I don't know, 800, 900,000 pages of mathematics by the time you've reached Calc 3. So it is understandable that you have not placed to memory every integration formula that you've been taught. Okay, that's not the game. Right? Listen, I've been studying math. Well, I started my PhD and became way too lazy to finish it, but I've been studying math for a long time. And I don't even know if I remember my multiplication tables, to be honest. Just be honest with you. Okay, so, but I don't, this is not a game of memory. This memory is great, but this is not the game that we're playing. So, if you have to look up formulas, don't fret, don't feel like you're behind. Now, if you don't know how to even apply a rule, then that's something we can remedy. Forgive me, but I'll have to lean on you to either come see me. Hey, I've forgotten how to do this or that, and then I'll teach it to you, reteach it to you. Heck, I might, if depending on what you ask, I might even have to take a second and look it up again real quick before I teach it to you. So, nevertheless, let's jump into the integration of vector valued function. Now, we, just like derivatives, we will integrate component by component. So that's easy. Most of your integration rules from Calc 1 and Calc 2 will all be applied. But what is different is that constant of integration, C, and this is important. Now, normally when you integrate, right, when you find an antiderivative, you get one constant of integration. Now, so here's a vector valued function. If you integrate a vector valued function, you are going to get a constant of integration for each component, and that is important. So, when you do integrate, although we integrate component by component, just remember that you are going to get multiple constants of integration. In fact, you'll get one for each component. So you have C sub 1, C sub 2, and in a second, C sub 3. Okay, so with that in mind, normally what, to just kind of let you know, normally what they will end up doing is, let's assume that you were to look this answer up in the back of the book. Well, you're not going to see plus C sub 1 plus C sub 2 plus C sub 3. They are going to turn all of those constants of integration into one constant. So it will end up looking like this. It will end up looking like, let me see, with the space that I have, let me focus on the constant part. So what they'll do is they will break up the f of t and the c sub 1 so that you have c sub 1 I plus c sub 2 j plus c sub 3 k. So notice that the constants will be bunched together as a vector, and then of course you would have the rest of these would r of t would be what's r of t would obviously be. I'm going fast, but maybe I'm going too fast. I just want to make sure. R of t would be the antiderivative, and we're going to let that be f of t plus g of t plus h of t, right? So notice you can imagine they just separate the function part from the constant of integration part, and then what they will do is they will just lump all of those constants into one C. So it might look something like this when you look it up in the back of the book. Okay, let's go ahead and do a few integration problems. Again, I will just assume prior knowledge of integration. I'm happy to unpack questions, but I'm not going to go back and teach you Calc 1 and Calc 2 unless you ask me to do so. So we're going to jump right in. So we want to find the indefinite integral of ti plus 3j. We're going to go ahead and integrate this component by component. So let's start with t. The integral of t would just be t squared over 2 in the I direction. So that goes here. And then let's integrate 3, and that's just going to be 3t. That'll be in the j direction. And then as far as I'm concerned, since we're doing indefinite integration, you can just write plus c. I just want you to be aware that this c right here, this means c sub 1 in the I direction plus c sub 2 in the j direction. That's what we mean when we write plus c. That would be our our indefinite integral. All right, you could always take the derivative if you wanted to double check yourself. Let's do one more. So now we're going to do a definite integration. So we are going to be integrating from 0 to 1. Okay. So what are we integrating? What is our r of t? Well, this, I have it checked here. All I've done from this step to this step is rewrote, instead of having the cube root of t, let's just go ahead and write that as t to the power of a third. Because in case no one has ever told you, if somebody were to ask you, hey, what is a square root? And you might say something like, oh, well, the square root of 4 is 2 and the square root of 9 is 3. They're like, and if they were to stop you and say, no. I'm asking, what is it? What is this symbol that we use for a square root? Well, long story short, if no one has ever, told you this, this symbol, all it means is that you are taking something and bringing it to the power of 1/2. This whole symbol is a way of writing a fractional exponent. That's all it is. The cube root means something to the power of a third. So that's just another. That's the notation for exponents that are fractions. That's all. All right, let's go ahead. We're going to go component by component. We don't have to worry about our constant of integration because obviously we're going to those are going to cancel out when we use our fundamental theorem of calculus. So let's just go ahead and, without a lot of elaboration, let's go ahead and set this up. So component by component, what do we got? We got t to integrating t to 1/3. This would be 3/4 t to the power of 4/3 from 0 to 1. That's in the I direction. All right, plus, well, if you integrate 1 over t plus 1, that is just textbook ln. So that just means ln of t plus 1. We're going to be going from 0 to 1. That's in the k direction. Almost there. So if you integrate negative e, or no, my apologies. If you integrate e to the negative t, that's going to end up being negative e to the negative t, 0 to 1. Okay, so what's going to happen right now is, we're just going to the notation that you remember from previous Calc 1 and Calc 2 was, say, f of a minus f of b, right? This is the first fundamental theorem of calculus. We're going to write that in this, since we're dealing with vector valued functions, it's going to be r of. So r of, I think I've got my a and my b mixed up, didn't I? So we're going from a to b, so it should be f of b minus f of a. Yeah, my apologies. This is what happens when you talk. Minus f of a. Talk and write at the same time. So f of b minus f of a, which just basically just means your upper bound substitute first minus your lower bound substituted. And now the notation that we're going to use, since we're dealing with vector value functions, is r. So r of b minus r of a. All right. Well, what does this end up giving us? Interesting. So let's start with, again, remember, component by component. So f of 1, it just ends up, for all of these, it ends up being f of 1 minus f of 0. Oh, my apologies. I just said I would use r, and then I didn't do it, right? So for all of these, it's going to be r of 1 minus r of 0. here we go. What do we get? Well, plug in 1 for, let's start with the I component. So r of 1 minus r of 0 gives us 3/4 I. All right, now your k components, r of 1 minus r of 0 gives us ln of 2 in the j direction. And finally, r of 1 minus r of 0 in for that last. Listen, did you see this mistake? You saw this mistake right here, didn't you? Why didn't you tell me something? Look, hold on. Did you see this? And you, how dare you, you didn't tell me that I put a K there instead of a J. That is your fault, not mine. Kidding, of course. Ready? And now let's just go ahead and finish it. So r of 1 minus r of 0 will end up giving us 1 minus 1 over e in the k direction. Okay. I tried to go through that quickly, and there was a few mistakes. A few mistakes. Okay. So what's the last problem from this section? So the last problem is let's now impose some type of condition on our problem. All right, so let's look at this last example. So notice now, of course, we have r prime. So let's add some context. Like, we know how fast something's moving, right? We know its velocity. But yet we're really interested in position, right? So what we're doing is we're going to be integrating to get back to a position function from our velocity function. Yet we know more information, right? So we have a little bit more information about this problem than the previous problems. And the question is, I wonder if this information is going to be enough for us to figure out our constants of integration. Because differential equations, we go through differential equations, and a lot of it can be cumbersome, it can be very time consuming, but a lot of it is, the techniques are, how do I find C? How do I find C? So let's jump in. Well, you kind of already know the game that we're going to play. We're just going to integrate. We're going to integrate r prime. That's the way we're going to start. And of course, we're integrating with respect to t. So let me go ahead and I'm going to go ahead and do that right now. So here is our antiderivative. So that's going to end up giving us, let's see here, we got cosine of 2t, so that should be 1/2 sine of 2t plus c sub 1. All right, let's go to our next component. So let's see here. That's good. If we integrate negative 2 sine of t, well, that's just going to be 2. It's going to be positive 2 cosine of t, because we already have a negative. We already have a negative here. So, all right. So let me write that. So that's going to be 2 cosine of t plus c sub 2. That's going to go in this j direction. Let me see if I can copy and paste this so I got more room. All right, ready? And now this actually be this would be I'd be impressed if you recalled just off the top of your head how to integrate that. But it does fit our definition for arctan. So that would be arctan of t plus c sub 3. That's in the k direction. Now, all I'm going to do is have some awkward silence for a second, because I just want to make sure that I integrated everything correctly. Okay, so we got 2 cosine of t plus c sub 2. Okay, so everything's perfect. All right, and now let's imagine that we would be stuck here. Even if you knew the velocity of an object, the calculus would allow you to integrate back to the position function, but do you see how unsatisfying this position function would be? Because we have a whole bunch of constants of integration that we don't have any idea what they are. So that doesn't quite help us if we're trying to predict the position of something, right? So, but because we actually have a little bit of information about our original function, we know that, so remember, what we just found right here, this would be r of t, because we started with r prime. Now, what we do know is that when t is 0, this is the vector that, this is the starting vector, right? So let me go ahead and write that initial condition. So the initial condition says r of 0 is equal to 3i minus 2j plus k. All right, beautiful. So now I want you to follow me here, because we're almost done. So what we're going to do is we're going to figure out what the left side of this equation is. Because what we're going to do is we're going to take, let me see if I can show you here. We're going to take this vector. We're going to write it here, except that we're going to plug 0 in for t. Does that make sense to you? I'll say that one more time. We're going to take that vector and we're going to place it on the left side of this equation, but we're going to make sure we plug 0 in for t. And what is that going to do? That's going to help us find our constants of integration. Ready? So here's what r of 0 looks like. So r of 0, I'm plugging 0 in for t. So r of 0, if I were to plug 0 in, let's see, r of 0, let's start here. So if I plug 0 in for t, sine of 2 times 0 is sine of 0. Sine of 0 is just 0, right? So that ends up being 0 plus c sub 1 I plus, ready, let's go to our j component. Now, at this stage, I'm plugging in 0 for t. Now, cosine of 0 is 1, so that would end up being 2 times 1. So 2 plus c sub 2. Ready? And now I'm going to be plugging in 0 one more time. Well, arctan of 0 is 0, so that just becomes 0 plus c sub 3. So j and k. All right. And now what I want to do is I just want to set these equal to each other and solve for c sub 1, c sub 2, c sub 3. So that's what I'm going to try to do right now with the space that I have. That has to equal. Here we go. So simple enough. Now we should be able to just via inspection, we should be able to answer C sub 1 is equal to, C sub 2 is equal to, C sub 3 is equal to. All right. Well, if you set I component equal to I component, well, 3i must equal 3i. So what must C sub 1 be in order to make that a true statement? Well, C sub 1 must equal 3. Likewise, if you set J component equal to J component, all right, so J component here, let's do it this way. J component equal to J component. Now, do you agree with me that in order to get -2, J, C sub 2 is going to have to be -4, because 2 minus 4 is -2. And finally, doing the same thing, C sub 3, you would just get 1. Okay. So beautiful. You have done some beautiful work here, but please do not get sloppy at the end, right? It's not your employer's job. It's not your customer's job to go back and fill in the C sub 2, C sub 1, C sub 3. It's not your client's job to do this extra work. You want to deliver a quality product. So all we have to do is just rewrite the integral with the new values of C sub 1, C sub 2, C sub 3. The good news is a heck of a lot easier when you have a stylus. I can go ahead and erase these. And now, so this would end up being C sub 1 is 3. C sub 2 is -4. And then plus 1. Beautiful. You now have a position function, right? You actually have a position function to go along with that velocity. All right, that will conclude 12.2. I will see you guys in the next video.